That's funny. It's more
We spoke last time about the GLRT, and this was it's a shorthand for Generalized Likelihood Ratio Test. This is a technique for detecting signals in a scenario where the signal itself is unknown or some parameter about the signal is unknown. And the GLRT referred to the particular technique which involved essentially replacing the unknown parameter or the unknown signal with a maximum likelihood estimate of the signal, and then proceeding to carry out a detection scenario that was just like the likelihood ratio test. So basically, the story was that H1 theta 1, if you have this PDF for the H1 hypothesis and this PDF for the H0 hypothesis, you might have these two parameters that are unknown. In fact, the two parameters might be the entire signal itself. So if these parameters are not known or the signal itself is not known, then what we would do is to replace these with their maximum likelihood estimates and then compare this to a threshold to detect. And this is the generalized likelihood ratio test scenario. So we started off with an example of a signal that had a single parameter that was unknown. I'll come back to that in a second, but I just want to present a slightly more general version of it first, and then we'll go back to that specific case. So the problem of interest that I want to describe to you is the following scenario. So let's say under H1 you have a signal x of n, which is S of n plus noise. And let's say this noise is 0 mean covariance sigma squared and IID for simplicity. And under H1, x of n is equal to W of n. And this signal here is unknown. For all samples, n equals 1 capital N. Okay? An important thing here is that I'm assuming that this S of n is unknown, but it's deterministic, so it's not random. It's some fixed signal, but I don't know what it is. And I want to detect it. So how do we carry out the generalized likelihood ratio test to do this? So let me write down this likelihood function, the generalized likelihood function, as a function of the data x that we have. So this is going to be the ratio of two exponentials, exponential minus 1 over 2 sigma squared sum, n equals 1 to capital N x of n minus s hat n squared. And the denominator would be minus 1 over 2 sigma squared sum plus 1 to n x squared n. Okay, and the coefficients in front just cancel out because they have the same variance. Okay? All right, so this S hat that I've put in here is, of course, what I mentioned up here as being the maximum likelihood estimate. So the first question to ask is, what is the maximum likelihood estimate of the signal given the data that you have? Okay, so if you just look at this scenario here, what is the maximum likelihood estimate? Well, what's S hat ml as a function of n? Any guesses?
It's unknown.
So what's the maximum likelihood estimate?
The average value.
Well, the average of m different.
Remember, what I'm trying to get at is the estimate for every n, right? And I have a bunch of signals x of n. So what am I going to average? If you suggested an average value, what would I average?
Average the previous data up to the instant n.
That would be one reasonable thing to do. In other words, take a window and average the last, let's say, m samples, and that would give you an estimate for the nth sample, and then move this window over, and so on. Okay, so that would be one estimate. But it turns out that would not be the maximum likelihood estimate. The maximum likelihood estimate would simply be obtained by minimizing this guy. Okay? So in fact, it turns out the maximum likelihood estimate at every sample is nothing but the sample itself. Okay? Because since the noise is uncorrelated, the other samples don't really give you any information about this particular sample. And because I have not made any other assumptions about S of n, I haven't assumed that S of n has some particular functional form. The best you can do is take your data point and say, that's my maximum likelihood estimate. Okay? So, if you then take a look at what you have, what you see is that if you take this and now plug it in here, and you simplify, what you will end up with is the following test. 1 over 2 sigma squared sum, n equals 1 to n of x squared, and this thing is going to get compared to some threshold, let's say gamma prime. Okay? Just plug that in. The numerator just goes away, basically, right? Becomes 1. And all you're left with is comparing the denominator to some threshold. And this seems a little strange, but in fact, it's really not that strange as soon as you kind of realize what it is that you're doing. So your test statistic, according to this, would be the generalized likelihood ratio test statistic is the sum, n equals 1 to capital N x squared n compared to gamma prime. Okay? What this is, it's an energy detector. Okay, so what you're doing is you're taking this data and you say, I don't know anything about the signal. But the idea simply is that if there is a signal, this energy would be higher. And if there's no signal, the energy would presumably be lower. Okay, so that's all that GLRT does in this case. And in fact, this kind of detector, which is computing the energy, is called an incoherent detector, because it doesn't care what particular order these samples occur in. In other words, the phase of the samples x of n doesn't really matter. All you're doing is you're squaring and summing the values. Okay, so this is it. You may have heard the term incoherent. Okay. So it ignores the phase. It's only computing the magnitude or the energy. Now, in contrast to this, let me remind you, if you happen to know what the signal in fact was, so in our earlier discussion, when we talked about matched filters, we noticed that for the same problem, the likelihood ratio test, when the signal was unknown, took the following form. The test statistic was the sum of x of n times s of n, n equals 1 to capital N, compared to some threshold. Okay? Now if you look at this, what's happened here is that here S has been replaced with S hat, which has been replaced by X, which gives you this. Okay? Now in this case, the values of the signal that you're measuring, the values of X of n, their phase in fact matters, right? Because X of n is getting multiplied by Sn, and this is in the literature, this is called a coherent detector. Coherent because it uses the phase explicitly. Okay? So does this make sense? Questions? Yeah.
If there is any correlations between S of n and S of n minus 1.
Right. Correlations between S of n and S of n minus 1. Remember I said S of...
And we know this correlation.
Mm-hmm.
This would be the case, and this would be the detector.
Yes, you would want to use it. Now remember here when I started, I indicated that S of n was unknown, but it was deterministic. In other words, it's not random. So perhaps the proper way to rephrase your question is, you don't want to talk about S of n as being correlated from signal to signal, because it's not random. So what you're saying is that if we knew the form of the function S of n, we should use it, and you're absolutely right. If you knew the form of the function S of n, then this would not be the maximum likelihood estimate. Then what you would do is you would use all the data X of n from n equals 1 to capital N to estimate those parameters. And then once you replace those parameters with their estimates, that would become the maximum likelihood estimate of the signal. Right? So for instance, let me be a little more explicit. So for example, if for the special case, let's say S of n is equal to alpha n plus beta n squared. Okay? If this is the case, then what you would do is you would take the X of n, now this is alpha n plus beta n plus noise, right? And you would write this out as X equals, say 1, 1, 2, 4, and so on, times alpha, beta, plus W. From this, you would estimate the maximum likelihood estimates for alpha and beta. You would get alpha hat and beta hat, which in this case, because everything is Gaussian, would simply be the least squares estimate. Then these guys would be replaced in here. Then S hat, the maximum likelihood estimate of S hat, would be alpha hat n plus beta hat n squared. Okay, this is not the same thing as that. So this is how you would use information about S of n if you knew it. Okay. So now let's talk about the example that we started off with last time. So this is a signal, again, it's kind of similar to the example I just gave you, where the signal is known except that some parameter related to the signal is not known. So let's say under H0 you have X of n is W of n, and under H1 you have X of n is A times S of n plus W of n. And again, simply this is Gaussian zero mean variance sigma squared. This S, this time we're going to assume that this is known, or we're going to assume that A is unknown. Okay? So this is a little different than the scenario we just considered. And so one of the questions one would like to ask is, you know, as I said before, the generalized likelihood ratio test generally doesn't have any optimality properties. So if you do what I suggested in the last couple of pages, you don't necessarily end up with a detector that has, let's say for a fixed false alarm, it has the highest probability of detection. But in some cases, you do. In some very special cases, you do. So for instance, one might ask, is for this scenario, is there a test that will produce the highest probability of detection for a given false alarm, regardless of the value of A? And it turns out that depending on how A behaves, the answer is yes. And that scenario is called the uniformly most powerful test. And so that's the example that I want to carry out now. Okay, so let's take a look at what this detector is going to look like. So first of all, let's just first assume that A is known. So let's consider just the likelihood ratio test that we did before when A is known. So this is the f of x given h1, the f of x given h0 compared to a threshold. And if we write this out, we get exponential minus 1 over 2 sigma squared sum equals 1 to n, x of n minus a, s of n squared, divided by the exponential minus 1 over 2 sigma squared sum x squared n compared to a threshold. Okay, so I'm going to simplify this. And I get minus 1 over 2 sigma squared sum is 1 to n minus 2a s of n x of n plus a squared n. That's compared to the log of gamma. Okay, to simplify it one more step, what you get is this: a times the sum x of n s of n compared to sigma squared log of gamma plus a squared over 2 times the sum s squared n. Okay, so this whole thing is a threshold. Now, I have intentionally left a on this side for a particular reason. If I want to simplify this one more step, I have to be careful. The reason I have to be careful is I have also intentionally not written down h1 and h0 here. Everything on the right-hand side, I know the signs, right? I mean, I can fix what lambda gamma is. That's my choice. I know the sign of that. Sigma squared is positive, a squared, and sum of the s squared is positive. What I don't know is the sign of a. Okay. So if a happens to be positive, I get a different test than if a happens to be negative. In other words, the choice of where I put h1 and h0 here will flip, right? In other words, I have two distinct tests that I have to be worried about here, depending on the sign of a. Okay, so let me write those out explicitly. So for a bigger than 0, have the sum equals 1 to n, x of n, s of n, compared to gamma prime over a. This would be choosing h1. If a is less than 0, this would be sum equals 1 to n, x of n, s of n, less than gamma prime over a. That would be choosing h1. Okay, they're quite the opposite in terms of the way you're going to make this comparison. Okay? Okay, so now if I take the scenario that I have and I imagine, suppose now that in fact I was dealing with a scenario where I didn't know the sign of A. Where I did know the sign of A. I knew that A was positive, but I didn't know exactly what its value was. Then what would happen is if I wrote down the generalized likelihood ratio test, now what I could do is I could divide by A without being worried, because I would know which direction the test is going to be performed. Okay? So in that case, I have a little bit more information than just, A is not known. Okay? So the bottom line here is, for this particular problem, if you did the GLRT without knowing anything about the sign of A, you couldn't say anything about its optimality. However, if I told you A is not known, but I know that it's positive, then what you have is a so-called one-sided test. It means I know that the parameter has to be to the left or to the right of 0, or to the left or right of some fixed value. Then I could come up with an estimator that in fact will give me a uniformly most powerful test. So if the sign of A is known, we get what's called a uniformly most powerful test. So let's write down the GLRT for this problem. So if I'm going to do that, then A hat maximum likelihood is arg min over A, the sum n equals 1 to n, x of n minus A, s of n squared. Okay? So this is just maximizing the likelihood, which is e to the minus this term. And so it's the same thing as minimizing this. And this is, of course, nothing but the least squares solution. And so if you take this, let's call this j of a, and you differentiate it, dj dA equal to 0, what you get is 2 of the sum x of n minus a, s of n minus s of n equals 0. And you simplify, you get a hat maximum likelihood is the sum x of n s of n divided by the sum s squared n. Okay? Another way to write this, by the way, is just with a simple vector notation. X transpose S, where these are the two vectors, divided by S transpose S. Okay. So this really, in fact, is like a correlation that you're measuring between the signal and the measurements. Okay, so let's take this and now put this into the GLRT function and see what we come up with. Okay, so minus 1 over 2 sigma squared, sum minus 2 a hat. Now this is going to be the maximum likelihood estimate, s of n, x of n, plus a hat squared, s squared n. Okay, and this is going to be compared to some threshold. So minus 1 over 2 sigma squared, minus 2a hat times x transpose s plus a hat squared s transpose s. Okay, again, this compared to some threshold. Minus 1 over 2 sigma squared. Now, remember what the definition of this a hat was. A hat maximum likelihood is x transpose s divided by s transpose s. So in fact, if you look at this, you can rewrite some of these terms simply in terms of the quantities that we just had. So let me rewrite this up here. So remember, a hat is x transpose s divided by s transpose s, right? Okay, so if we simplify all of this, what we get is minus 1/2 sigma squared minus 2 a hat squared s transpose s plus a hat squared s transpose s. Okay? So I'm just replacing some of these things so that I get everything in terms of a hat. Okay? And then you simplify this, you get a hat maximum likelihood squared compared to 2 sigma squared log of gamma divided by s transpose s. Okay. Or another way to write this would be absolute value of a hat maximum likelihood compared to the square root of this quantity. Okay. Now what you see here is kind of interesting. This is the test. This is the GLRT test. Right? What it's showing you is that the GLRT test, in fact, gets rid of the sign of A. Okay? I mean, what I just showed you was that if we just carried things out ignorant of the sign of A, we would run into trouble. Well, one of the things that GLRT will do in this case is we'll come up with an estimator that will, in fact, square A hat or take its absolute value, because it is entirely possible that if you just did maximum likelihood without taking care of that, then it would end up with a negative number. And this is telling you to basically get rid of the sign when you do the test. Okay? And of course, another way to write this, if you wanted to write it in terms of the data itself, this is X transpose S squared compared to 2 sigma squared log of gamma times S transpose S. Okay, I've just simplified everything. If you write this as this thing squared and then you move things around, this is the test that you get. Okay? So it's interesting because what you're doing here is this is in fact the coherent matched filter, except that the output is being squared before it gets compared to the threshold. Okay? Why do I bother going through all of this stuff? There's a very important reason, which is when you look at a problem, you know, as simple as this, right? This is nothing. This is just, you know, a signal that's known and A that's unknown. You think, well, this is trivial, right? I mean, there's nothing interesting in this problem. But when you start actually working it out, you realize it has a lot of really fine things that you have to pay attention to. And this is a very common thing in statistical signal processing. Even the simplest problems can have a lot of complex things going on inside them that you have to pay very careful attention to. And oftentimes the mistakes that people make are because they assume that because a problem looks on the surface very simple, the interpretation of the solution and the properties of the solution are going to be just as trivial. And that's almost never the case in this particular business. And I'm talking specifically of the case where you have unknown parameters and you're trying to do detection. Okay? You have to be very, very cautious with the kinds of things that you do. All right, so that's one set of scenarios. Another set of scenarios where you don't have global optimality. In other words, you don't have optimality for just any underlying value of the parameter. You do have optimality for certain cases. Okay? So this is what we call locally optimal detection, or locally optimal test. Okay, so what's the idea here? The idea is you have something kind of like what we just talked about, except for the fact that the assumption we're going to make on A is that it's very small. Okay, so let's say you have two scenarios, again, H0 and H1. Under this case, you have PDF of X given H0 and some unknown parameter theta 0. In this case, PDF of X for H1 with some unknown parameter theta 1. And what we're going to do is we're going to assume that these two parameters are really close to each other. Okay? So we're going to assume that theta 1 minus theta 0 is small. And we're also going to assume that theta is bigger than theta 0, or theta 1 is bigger than theta 0. So this is kind of like what we did before. In other words, we're going to assume that the parameter is positive, for example. Like, so if this was A, we're going to assume that theta 0 is 0. We're going to say one-sided test. So we have a one-sided test, and we have this small distance between the two parameters. So let's see what we can do here. So if we look at the Neiman-Pearson test now, so this is a likelihood ratio test. What we have is PDF of X given theta 1, PDF of X given theta 0, compared to a threshold. We can take the log of both sides of this. Log PDF of X given theta 1 minus log PDF of X given theta 0 is compared to the log of gamma. Okay. Now, the next step is simply going to use this property. if theta 1 and theta 0 are really close to each other, then what I can do is I can take this guy and write it as a Taylor series around this other parameter. Okay? So because this small assumption is true, I use a Taylor series approximation, and I write this. Log p x given theta 1 is approximately log p x given theta 0 plus p x given theta evaluated times theta minus theta 0. And this derivative is evaluated at theta 0. Okay? I want to warn you about the meaning of this. This is not a Taylor series around some small value of x. Okay? This is a Taylor series around the value of the parameter. So this is something you have to be very careful about, because this actually is a global approximation of the function p of x. Okay? So it's as if you had, let's say you had a polynomial, right? ax plus b, or ax squared plus bx plus c. And what you're doing is you're taking the a, b, and c, those coefficients, and you're slightly perturbing them. And you're going to get a new polynomial of the same order, maybe, but now that polynomial is going to behave differently everywhere. Okay? So we can now use this Taylor series to simplify the log likelihood ratio test. If I simply take this approximation and just plug it in here, what I'm going to get is, so I just plug this in here, I get log p x given theta 0 plus this derivative minus log p x given theta 0. Now if you see, these two pieces are just going to go away, right? They just cancel each other out. And what I'm going to be left with is okay. And now what I would like to do is I would like to do a test based on this. And if I want to do this test in such a way that it doesn't depend on the sign of this guy, now I need to keep that assumption. Okay? So with the positivity assumption, then I get log of p x given theta, p theta evaluated at theta 0 compared to log of gamma divided by theta 1 minus theta 0, and you can call this sum of the threshold. Okay. So this is basically a locally optimal test now for all values of theta that are close, theta 0 and theta 1 that are close to each other. Now, typically what we do is we also normalize this left-hand side for reasons that I'll just describe to you in a second. If you remember this, this guy here is basically the score function that we talked about before, right? And what we had was that the expected value of the score function is 0 and all that stuff. We also talked about the variance of the score function, which was essentially the Fisher information matrix, right? So we know that this guy has 0 mean, and we know what its variance is. So one thing that's convenient to do is actually to normalize this left-hand side by the Fisher information so that this thing basically behaves like something that's 0 mean and has unit variance. Okay? So what we do is you normalize this. The test statistic, what we call LMP, the locally most powerful test statistic based on this, then is this numerator. And then you divide it by the square root of the expected value of d theta squared, evaluated at theta 0. So this is basically the square root of the Fisher information. So what you're doing is you're taking the variable and you're normalizing it by its standard deviation. So now the variance of this whole thing is going to be 1. Okay? So this normalizes the variance. Okay, and then what you're going to do is you're going to compare this to a threshold. And this is called locally optimal, or locally uniformly most powerful test. Okay? And this is much more general than the other case that we just talked about where you just had a parameter A, right? I mean, I didn't give you any functional form for these guys. It can be anything. Just as long as theta 1 and theta 0 are close to each other, and you happen to know that one is to the left of the other, then you can do this test locally and get locally an optimal test, which means that for values of the parameter theta that satisfy these conditions, you can fix a false alarm rate and get the maximum possible probability of detection. Okay? That's pretty nice. I mean, given the fact that the unknown parameters are, you didn't get rid of the unknown parameters. They're there. You're sort of dealing with them in a particular way. Okay, so if we in fact look at this asymptotically, when you have a lot of data, so when the number of samples goes to infinity, or when the noise kind of asymptotically approaches 0, then this test statistic, this is how we write it, asymptotically has the following distributions: normal, zero mean, and unit variance under H0. And it's normal with a mean mu, I'll tell you what that is in a second, and variance 1 under H1, where mu is the square root of the Fisher information measured at theta 0 times theta 1 minus theta 0. Okay? So basically, when you have lots of data, it turns out this local test will give you a statistic, will give you a test statistic that's asymptotically normal in these two cases. So you, in fact, not only do you have an optimal test locally, you can also characterize its performance, at least asymptotically. And using these two, you can compute the, you can in fact exactly compute the PD and the PF for the asymptotic case and plot the ROC curve and so on. Okay? Yeah.
And the asymptotic case requires having a large number of data.
A large number of data, that's right. A large number of samples. Or equivalently, having the variance of the noise approach 0. Those are essentially the same in most cases. Okay, so one application of this is so-called correlation testing, which turns out to be very useful in lots of different applications, for instance, communication and so on. And the basic idea here is that you have a sequence of data, and so let's call it x0, x1, say x n minus 1, and these are vectors, okay? And there are the distribution of these guys. Well, let me write it explicitly. So this is x1 of n, x2 of n. Okay, so each one of these is a two-dimensional vector. The distribution of these guys is normal with 0 mean, some covariance c, and c is like this: 1 row, row 1. In other words, we know that these elements here have unit variance, that's these two terms, and we know that they are correlated with some correlation rho, but we don't know what rho is. But of course, you know that the correlation coefficient is a number that is between -1 and 1, right? So you already know that it's small, okay? So here's what we're going to do. We have the following problem. Under H0, we're going to assume that rho is equal to 0. And under H1, we want to test whether correlation is positive. Okay. Now again, we can't do we can't do anything but a one-sided test. So we can test whether rho is positive, or we can test whether rho is negative. But we can't test whether rho is equal to 0 or rho is not equal to 0 and expect optimal performance. Okay. So here we're also going to assume that rho is small. So how do we proceed? Well, basically the scenario that we just talked about here is what helps. So if you compute the log of the likelihood function as a function of rho and differentiate it with respect to rho, evaluate it at rho equals 0, which is this is your reference point. This is minus the sum x transpose n c inverse x of n, like that. Okay? And if you remember from some time ago, we had that these types of covariance matrices are easily inverted. You just write them like this: 1 minus rho 1. Okay. All right. So now, if I take this C inverse and I plug it into here, what am I going to get? So this turns out to be equal to the sum equals 0 to n minus 1, x1 of n times x2 of n. Okay? Which in retrospect is not terribly surprising, because what you're trying to test is correlation, and what you're measuring is something like a correlation in this numerator. But we also want to normalize it in the way that I just described here with this denominator. So we're going to calculate, I'm just going to show you what the Fisher information matrix, or the Fisher information, it's not a matrix in this case, looks like. So this I of rho turns out to be n times 1 plus rho squared divided by 1 minus rho squared squared. And so if you evaluate this at 0, I of 0 is equal to just n. Okay? So you simplify, and so your test statistic, the locally most powerful test, as a function of the data, is then 1 over square root of n times the sum x1n, x2n, and this gets compared to a threshold. Okay? Now, in fact, this thing here, remember that x1 and x2 both have variance equal to 1, right? So this here, in fact, is an estimate of the correlation. Okay? In fact, if you computed a maximum likelihood estimate of the correlation from this model, this is exactly what you would get. So what this is telling you is you're going to compute the correlation function, and you're going to compare it to a threshold. Or another way to look at it is this is basically n. This is the test, okay? And asymptotically, the distribution of this guy, T lnp of x, asymptotically will be normal 0, 1 under H0, and normal with mean square root of n rho comma 1 under H1. Okay? Now, how do you, suppose you want to actually measure the performance of this guy and you want to do a ROC curve. Yes?
Can you show the previous page for a second?
Yeah.
Okay.
No question?
Yeah.
Okay. Now, you have if you wanted to now take this and actually compute a ROC curve for this, maybe look something like this. You have these two quantities, but you also don't know what this rho is, right? In other words, this is something that was not given to you. You're just trying to test whether it's positive or 0. Well, then what you have to do is you have to plot this curve for different values of rho. Okay? And so, for instance, if rho is really, really close to 0, then what happens is these two get really close to each other, right? So what's going to happen is your performance, this is the chance line. If rho is really, really close to 0, your performance is going to be really close to this line, right? And then you're going to plot it for larger and larger values of rho. And as you get close to rho being equal to 1, you can't expect this to give you a very good idea of the performance anymore, because now you're getting away from the approximation where rho was very close to 0, right? So again, you don't want to fool yourself with a performance. You don't want to do this analysis and then show this for rho equals 0.99, because that may not be a very exact performance, because rho approximation is no longer as valid as it was when rho was full. So ironically, the optimality conditions are only valid when rho is small, which is the hardest cases to distinguish. Okay? I mean, that's kind of, you would expect in the easier cases to have the optimality result, but kind of the reverse happens here. It's in the hardest case that you can prove optimality locally. Okay, so the next thing I would like to do is talk about an example of GLRT, which I believe that some of you, most of you, if not all of you, are familiar with, at least in one form or another. And this is, how many people have heard of spectrograms? Spectrometer, spectrograms, spectral analysis is when you look at FFTs, right? You take a signal and you want to see what components there are in that signal. The signal is always measured with noise, right? So what do? You take it and you plug it into a spectrum analyzer, or you just take it into MATLAB and take FFTs and you plot the magnitude of the FFTs. So it turns out what you're doing is GLRT. Okay? And I'm going to show you what I mean by that specifically. So here's the case of a signal which in this case is just, let's say, Gaussian noise. And under H1, it's a sinusoid. A times cosine 2 pi f0n plus some phi plus W of n. Okay? And let's assume that the things that we don't know for the time being are A and phi. So this is the phase. This is the phase shift. And this is the amplitude. This here is the frequency. But for now, let's assume we know that. But later on, I'll show you, you can also assume that that's not known. So you don't know the phase, you don't know the frequency, and you don't know the amplitude. But for now, let's just stick with that and see what happens. So if we do GLRT for this, EDF of x given H1 and the parameters A hat and phi hat divided by EDF of x given H0, and then we compare that to a threshold. Okay. So what's the maximum likelihood estimate of these parameters? So we can do this simultaneously. Say A hat and phi hat are arg min of a function j, which is a function of A and phi. And j is this. It's the sum or all the data, I'm going to assume that I have n equals, say, 1 to capital N. So sum x of n minus a cosine 2 pi f0 n plus b squared. Okay? And so this is unknown and this is unknown. Okay. So how do we handle this estimation? So we have two unknowns. One of the ways to do it, to make things a little simpler, this is obviously linear in A and nonlinear in phi. One way to do it is to expand this cosine using a cosine sum formula and define the following two other parameters. Alpha 1 is A cosine phi, and this define alpha 2 as minus A sine phi. Then the optimization will be carried out in terms of alpha 1 and alpha 2 now, and this will be the sum x of n minus alpha 1 cosine 2 pi f0 n minus alpha 2 times sine 2 pi f0 n. Okay? And then this whole thing squared. So now what I've done is I've just played a trick. I've turned a problem that was linear in A and nonlinear in phi into a problem that is linear in both alpha 1 and alpha 2. So I can now solve this. This is just a simple least squares problem, and I can solve it, no problem. Okay, so how do we do this? Then this cost, j of alpha 1, alpha 2, this is just the norm of some vector x minus h times alpha squared, where alpha is alpha 1, alpha 2. X is, of course, all the data strung up into a vector. And h is 1, 0, cosine 2 pi f0, sine 2 pi f0, and so on up to cosine 2 pi f0 times n minus 1, sine 2 pi f0 times n minus 1. Okay, so it's two columns. Okay, so the solution of this guy then is alpha hat equals h transpose h inverse h transpose x, and this approximately is equal to 2 over n sum x of n cosine 2 pi f0 n, 2 over n sum x of n sine 2 pi f0 n. Okay. So then if you take this, and from this you want to estimate the amplitude, it's easy, because the amplitude in fact is the square root of alpha 1 hat squared plus alpha 2 hat squared. Okay? And this turns out to be 2 over n times the magnitude sum x of n. You rewrite this as exponential minus 2 pi f0 jn. So I've just written everything out in terms of complex exponentials, putting together the sine and the cosine. So if you take a look at this now, what exactly do you have? What you have here inside is the Fourier transform. Okay? You have simply the sequence x of n, and you've taken the Fourier transform of it, and you're looking at it at every frequency. In particular, you're looking at it at this f0 where you expect it to be. You're taking the magnitude of that Fourier transform, and you're looking at it. So suppose I were to take the signal x of t and FFT it, and then compute the magnitude of the FFT and plot it, what would it look like? So this is, say, 0. This is the frequency axis. This is f0, and this is minus f0. Okay, what would the FFT look like? It'll look like this, and then here you'll have a big bump, and maybe you'll have some other stuff here, and then here you'll have another big bump. Okay? And this height is exactly a hat. Okay? So maximum likelihood estimate is in fact the magnitude of the Fourier transform that you got. And the process is that you took the signals, you FFT'd, your amplitude, and you read off the number. As far as the phase is concerned, the unknown phase is the arc tangent of minus alpha 2 hat divided by alpha 1 hat. Okay? And now we can take these numbers and plug them into the GLRT expression and see what we get. So the log of the generalized likelihood function, this is the likelihood function with the maximum likelihood things plugged in, is minus 1 over 2 sigma squared. The sum minus 2 x of n a hat cosine 2 pi f0 n plus v hat, sorry, plus the sum a hat squared cosine squared 2 pi f0 n plus v hat. Okay, this whole thing. And in fact, if you now go back and look at this expression here, what you'll see is you can rewrite this in terms of alpha 1 and alpha 2. In fact, I'm going to skip a couple of steps of algebra, and this turns out to be n over 4 sigma squared times alpha 1 hat plus alpha 2 hat. Okay? Which, again, I can rewrite it in terms of the Fourier transform. It's 1 over sigma squared times 1 over n times the sum x of n exponential of minus 2 pi j f0 n, and this whole thing squared. Okay? Now, if you look at this, what you have here is this is the magnitude squared of the Fourier transform normalized by the variance of the noise. So this basically is the spectrogram. This is the magnitude squared of the Fourier transform. So what it's saying is if you want to detect the presence of a signal, what you're going to do is you're going to take the discrete Fourier transform, you're going to take the magnitude squared of it, you're going to normalize it by the variance of the noise, and you're going to compare to a threshold. So in other words, this picture that I drew for you, something like this, what you're going to do is you're going to take this and you're going to threshold it. And if the peaks go above the threshold, signal detected. If the peaks are not above the threshold, signal not detected. And that's exactly what we do when we eyeball it, right? You put it into spectrogram where you do MATLAB, the peak comes up and says, oh, well, it's high enough that the signal detected. Okay. And how do you set the threshold? Well, then you have to do this analysis with the performance. If you assume the amplitude is really small, for instance, then you can do a locally optimal test. Okay. Now here's where things get interesting. If you know the amplitude is positive, right, and you know that it's really small, you can do a local optimal test. There's all kinds of generalizations of this that of course we can do as well. We can also assume that the frequency is not known. So let's say the unknowns include the frequency. So let's say A, phi, and f0 are all unknown. I already said that, didn't I? So what you want to do now is you take what you had before and you also maximize over the frequency. Okay? So what ends up happening is you look at max over f0, PDF of x given h1, and you plug in a hat, phi hat, and f0, divide by PDF of x given h0. Okay? So what this means is all you're going to do is your spectrogram is not going to look so perfect like this one did, okay? Especially if your signal is weak, what your spectrogram is going to look like is more something like this, okay? And what you're going to do is you're going to maximize this guy. So what you're going to do is you're going to go to the largest peak that you can find, and at that peak do a threshold test. Okay. There's still something else that you might know, which is the start time of the signal. Okay. So suppose yet another unknown. Might be, so let's say I capture this data, x of 0, x of 1, x of n minus 1. And let's say x of n minus 1 is some huge number, right? I captured 100,000 samples. Okay? It's entirely possible that the signal that I'm looking for, this sinusoid, wasn't there the whole time. Okay? So suppose that the first, let's say 100,000 samples, the first 90,000 samples, there was nothing. And then between 90,000 and 95,000, there was a signal. The aliens sent us a cosinusoid, right? And then they stopped. Okay? So how do I detect that? Well, what you have to do is you then do exactly what we just talked about here in a windowed fashion. Okay? So you don't take the entire 100,000 and do a Fourier transform on it. What you do is you take a window of, let's say, 10,000 samples, and you slide that window of 10,000 samples across your 100,000 sample, or you just do this on an ongoing basis online, and you plot something that basically does the following. It assumes this n0 is, so let's say this is the start time. Okay. You might also not know the end time, but let's put that aside for a second, okay? So let's say you do a plot like this, where this axis would be the frequency, right? So let's say across different f0s. And what you're going to get in this plot, you test for start times from 0 to whatever 90,000. And what you're going to get here is something that it's going to be a surface. Each one of the columns of this surface is going to be one FFT, right? Over a small window of, let's say, like 10,000. And then you're sliding it across. So what ends up happening here is, if you're lucky, you might end up getting something that has a peak. And let's say that peak has some contours like this. And then at the peak of this contour, here, you're going to get an N0 hat and an F0 hat. Okay, this is going to be the estimate of the frequency, and this is going to be the estimate of the start time, maximum likelihood estimate of the start time and the frequency. Okay, and you might in fact have multiple signals, right? Maybe it's not just one alien that's sending you a message. Maybe it's a whole bunch of aliens. Well, if you did this you might get another peak here. Okay, and now you can detect multiple signals. Of course, things get more complicated as you do this. But the bottom line is, the idea here is the Fourier transform is not going to be computed over the whole thing now. The Fourier transform, well, let me draw a picture here. I'll write it out for you. What you're going to do is sum, say x of n exponential minus 2 pi j f0n. Now what you're going to do is n equals n0 to n0 plus m minus 1. So you're going to have some length, signal of length m that you're going to assume. Okay? And m may not even be known. And then you're going to take the magnitude of this squared, and you're going to maximize this over the frequency and the start time that you don't know. And this here is what we call the short time discrete Fourier transform. And this is exactly the plot that we just did here. Okay? So the bottom line is, what you're going to do is you're going to take a window like this, And then you're going to slide this window across your data, and slide it again, and so on. And plot that. This is also called a spectrogram. What about some examples of this? Well, I already mentioned a very prominent example of this, which may have sounded funny, but it's true. This is how scientists look for aliens. Okay? So if you go to Mountain View, there's the SETI Institute. SETI stands for SETI, Search for Extraterrestrial Intelligence. And this is what they do. They take radio telescopes from all over the world, just pointed at every angle in the sky, and they're looking for sinusoids. Now don't ask me why are they looking for sinusoids. I think that's kind of strange myself. But the idea is that they think if there's something out there, then what it's doing is it knows about sinusoids because they're, in some sense, the right thing to be sending across. And it's going to send us these things. And what we don't know is we don't know what frequency they're sending. We don't know when they're sending it. We don't know how long they're sending it for. We don't know which direction it's coming from. So what they do is they just sweep these radio telescopes in every place in the sky that they think is likely to be, they're likely to be these kinds of signals, and they're just continuously doing a detection, basically. And occasionally they get false alarms, and they haven't quite detected anything yet, but hasn't stopped them. But I mean, all joking aside, this is literally what they do. Okay. Another maybe less strange example of this is this is how submarines detect other submarines. Okay, so if you're a submarine sonar officer, this is what you do. You're listening in the ocean for sounds. And depending on what the frequency of the sound is that you detect in your spectrogram plot, in this kind of plot, okay? You're also looking at directions in those cases. You're looking at direction, you're looking at depth, you're looking at the frequency of the sound that you're getting, you're looking at when it started and when it stopped. And for instance, by looking at the frequency of the sound that you're hearing, you can tell what kind of submarine it is. Okay, is it an American submarine? Is it a Russian submarine? You can even tell what gear its engine is in. Okay? How fast it's going, all of these things you can get by looking at these kinds of information. And of course, in the ocean, there's not just the sound of submarines, there's zillions of other sounds. Right? So this thing's not going to look very pretty, it's going to have all kinds of noise in it, and so there's a lot of processing that has to go on to do this in a clear and clean fashion. Okay? And so that's what I just described to you, is a passive scenario where all you're doing is listening. Then you have active sonar, which is you're not just recording, you also occasionally send a ping, which is just a sound. It goes out and it bounces off of all these different objects that are there. And then you listen for the reverberation. That's a much better way to detect, right? Because now you know a signal. You know the signal that you sent out, so maybe some cosine, you know its amplitude, you know its phase, you know its frequency. And so now you know what to be listening for. Of course, if you do that, then you're giving up your location, right? So somebody else might be listening. So you want to stay as quiet as possible. Anyway, there are many, many applications of these things in all kinds of different areas of engineering. But the beauty of this is GLRT. Okay? Yeah. Did you have a question?
How would you generalize this to wavelet decomposition?
Well, the wavelet decomposition is just using a different transform. So the idea is, if your signal is here, we're assuming that the signal is a cosine, right? What's the best way to represent a cosine in a Fourier transform basis? Okay, because you get a single number, you get a single coefficient that tells you that signal is present. If you're looking for signals that are more complicated, they're not just cosines, let's say some other signal that is not easily expressed by a Fourier series. Let's say, for instance, signals have discontinuities in them. Okay? Then what you're going to do is you're going to measure, or you're going to express your signal on a different basis. Here, if you have multiple cosines, you would just write a sum of a bunch of cosines, and the same detection problem would hold. So if your signal is something else, you can express it in a wavelet basis. Then instead of this kind of plot being a Fourier transform plot, it would be a wavelet transform plot. So you would look at the coefficients of the wavelet transform as heights above this basis. Okay? And then if those coefficients in that particular basis are strong enough, that will lead you to a detection. It doesn't have to be wavelet, it can be any basis. So you have some function f of s, and you're going to express that f of s in some basis. Then you're going to estimate the coefficients in that basis and compare those to a threshold, compare the function based on those parameters to a threshold. And that's the same framework as this.
So the GLRT simply looks at the coefficients of n is basis invariant?
Well, I wouldn't say it's basis invariant. Your detection test is going to be a different test depending on how you write your signal, right? But the point is, whatever your signal basis is, GLRT can work with it. Let me write it down. Maybe this will help understand it. So let's say your signal x of n measured. So let's say you have s of n plus w of n, right? So in our case, we wrote s of n as a single sinusoid. It doesn't have to be a single sinusoid. You can write any number of sinusoids. In fact, you can write s of n as the sum of, let's say, lambda I times phi I of n for I equals 1 to k. Okay? What I've done here is I've expressed the signal s of n in a basis phi of n. Now, if you're talking about the Fourier basis, then these functions are cosines and sines, or complex exponentials, more generally. Right? If you express s of n in a wavelet basis, then these guys would be wavelets. Okay? Whatever you do, the point is there's a bunch of unknown coefficients. Okay? GLRT will do the following. You will estimate the lambda I hats, which are the coefficients, using maximum likelihood. From this, you would write s hat of n as the sum of lambda I hat phi I of n. And then this would get plugged into the p of x given h1, p of x given h0. And then you would compare to a threshold. Does that make sense? So this estimate is what would go into here, where the unknowns are. So you could write here p of x given h1 comma theta 1. And what's theta 1? Theta 1 in this case are these coefficients. Okay? It just so happens that for the Fourier basis, this is a well-known thing. The short-time Fourier transform and the spectrogram or so on, these are all well-known. If you want to use wavelets, that's fine too. Okay. I can tell you for the applications that I gave you, where you expect to see sinusoids, then you want to use sinusoidal basis, which is a Fourier transform. Okay, other questions? No? Okay. So let me give a quick summary of where we stand so far with respect to all the stuff that we've done in the class. So we first started talking about detection. And the likelihood ratio test was the most general framework that we considered. Then we talked about a Bayesian approach where you assumed that you had a probability density function. The Bayesian approach basically assumed that you had some likelihood associated with each of the hypotheses that you were trying to decide amongst. And also what we did is all of these discussions were with respect to a single pair of hypotheses, so just two. But the discussion is not limited to that. You can talk about detection as something that's trying to compare amongst m different hypotheses. Of course, the calculations get more complicated, the bookkeeping gets more complicated, but the bottom line is not that different. So, for instance, if you had, let's say, 3 hypotheses. Well, let's go back to the 2 hypotheses. When you have 2 hypotheses, the likelihood ratio test, what it does is it divides the space into 2 pieces, right? If your data falls into this piece, you pick H1. If it falls into the other piece, you get H0. Now, if you have 3 hypotheses, then you have to divide the space into 3 pieces, okay? And if you have more hypotheses, then what happens is that you're going to have more and more pieces that you're going to have to carve the space into. And if your data point happens to fall in a particular part of that space, then you detect that particular hypothesis to be true. Okay? So the general idea is really not that different. It's just that the bookkeeping gets more complicated. So we talked about these. So this assumed that you had probability of HI, and this assumed that you didn't. Okay, and then we talked about estimation. And in estimation, we discussed the maximum likelihood, which again did not assume you knew anything about the parameter that you were trying to estimate, aside from the fact that it was not random. Okay. Maximum a posteriori assumed that you knew something prior about the distribution of the unknown parameter. In other words, here you're assuming that the unknown parameter is itself random, but that it has some distribution that captures it. We also talked about least squares, and least squares didn't really make any assumptions about the distribution of the data. You're minimizing a quadratic cost function, and whatever that happens to give you is your least squares estimate. We also talked about how least squares can coincide with the maximum likelihood estimate in the scenario where the noise is Gaussian. Okay? So if the noise is Gaussian and white, then the standard least squares coincides with the maximum likelihood estimate. If the noise is Gaussian and correlated, then weighted least squares coincides with maximum likelihood. We also talked about when least squares gets regularized. Regularization adds an additional penalty to the cost function that you're minimizing. And it turns out that additional penalty is equivalent to assuming a prior density. Okay? In other words, I'm not sure we went through this very clearly, so let me just kind of give you a little bit of reminder about this, because I think this is quite important. So if you have the least squares criterion and then you add something to it, let's say R of theta, okay? And now what you want to do is minimize the combination of these. This is what we call the regularizer. This is the thing that keeps the solution of this from blowing up because, let's say, H might be unstable. Okay? So if you look at this in the context of map, you can also think of this equivalently like this. So I can write P of x given theta as a Gaussian. Okay? So this would be, let's say, a normal with mean h theta and let's say covariance sigma squared identity. Okay? So if this is the case, then this is going to look like some exponential times minus 1 over sigma squared times the norm of x minus h theta squared. Right? This is going to be proportional to something like this. And suppose I now assume that P of theta also has a distribution which looks like this. It's the exponential of minus R of theta. Okay? And so, some normalization coefficient in the front to make sure that it's all sums up to 1. Okay? So if I take these two, and now I look at P of x given theta times P of theta, or equivalently, I look at the log of P of x given theta plus the log of P of theta. Okay? If I want to do a maximum a posteriori, I have to maximize this guy, right, over theta. Okay, so that's equivalent to maximizing this guy. And now if I take the log of these things, I have something that looks like 1 over sigma squared norm of x minus h theta squared plus r of theta. Okay, so maximizing this is equivalent to minimizing this over theta. So now suddenly you see what I have here is a stabilized least squares problem. So what we did is, when I wrote down this regularized least squares problem, this is more general in the sense that I'm not making any distributional assumptions. But if you start with a Gaussian assumption, I mean, this is not actually exactly Gaussian because this guy can be anything, right, as long as it's positive. Okay, so this is just some penalty. This is a particular type of, it's called a Gibbs prior. Anything that looks like e to the minus something positive can be used as a prior. Okay, so then you end up with this. In other words, the regularized least squares problem happens to coincide with the maximum a posteriori solution when the data is Gaussian distributed and the prior has this type of Gibbs distribution. Okay, this is a very important thing to remember, because sometimes you write something like this down and then you want to interpret it. What does it mean? Okay, and the meaning comes from the statistical interpretation. Okay, so we did the detection, we did the estimation, and then we went back to the detection scenario, except that now we assume that we didn't have any parameter, we had some unknown parameters, and this is what we call composite hypothesis testing. And this is, you write the generalized likelihood ratio test, PDF of x given h1 and theta 1 hat, PDF of x given h0, theta 0 hat, where these are the maximum likelihood estimates. As I mentioned, there is nothing to stop you from replacing these with the least squares estimate or the maximum likelihood estimate or any other estimate you like. However, for these other estimators, we don't have any results in general. I mean, there are some results, but they're not obvious results. Okay? So what we call the generalized likelihood ratio test is specifically replacing these with maximum likelihood estimators. Okay. One other thing that I want to warn you about is that these quantities are not the numerical values of the maximum likelihood estimate that are getting plugged into here. These are the expressions for the maximum likelihood estimator that are getting plugged into this equation. Is that clear? In other words, what you're going to do is you're going to write theta 1 hat, let's say it's g1 of x, right? Some function of x, and theta 0 hat is g0 of x, again some function of x. What you're going to do is you're going to plug this into this equation, and what you're going to end up with is a function of x. Same thing here, you're going to plug this into the denominator and get a function of x. Then once you have your data, you're going to plug in x. Okay? This is a slightly subtle point, or maybe obvious to some of you. If you just compute this and you say, okay, my theta 1 now given my data is just a single number, and I'm just going to plug this in here, but now I'm going to keep my x as a free parameter, and I'm going to wait for new data to come in. Wrong. Okay? X has to be computed in a sort of abstract way given a vector x. Okay? Theta hat has to be computed given a vector x. You plug it in, you simplify, you get a test statistic based on x. Then you plug in the data that you have, and you compare to a threshold. Okay, so what are we going to do for the rest of the lectures? Well, the next topic that I'm going to present is going to be a different way of estimating, a different way of looking at estimation. So far we've looked at estimation as you've got a signal and there's some unknown parameter and you want to estimate the unknown parameter. The next thing that I want to do, which again applies to all of these ideas that we've talked about so far, is something called Bayesian minimal mean squared error estimation. And what that has to do with is a very general framework which says the following. Look, you have two random vectors, okay? You have x and you have y. And these two random vectors come from some distribution p of x and y, okay? And what you'd like to do is to estimate x based on y, or estimate y based on x. Okay? In other words, you have two measurements, x and y, and what you want to do is just improve the value of x that you have based on this y that you got, because you know that they're related to each other. Okay? So you're going to try to extract some information from the other measurement towards this guy. And underneath them is a probability density function, which for now we're going to assume is known. And it turns out that even if it's not known, there are some interesting things you can do. Okay? So this is called Bayesian minimal mean squared error estimation. We're going to cover that. We're also going to cover some of the things that kind of follow from it, like the Wiener filter and so on and so forth. Once we've studied these different techniques, this Bayesian minimum mean squared error, you'll see what is the difference between maximum likelihood, maximum a posteriori, Bayes minimal mean squared error, least squares, and we'll be able to kind of visualize all of these and kind of decide why is it that we use one versus the other. Okay. And then finally, what we're going to do is go to the place where these probability density functions are not even known. Okay? So let's say I give you two quantities, x and y. I know these quantities are related through some probability density p of x and y, but I don't know p of x and y. Not just that I don't know some parameter in x and y. I actually don't know p of x and y. All I've got is a bunch of measurements of x and y. So what am I going to do now? If I want to make a prediction of x based on y, I have to do two things. I have to actually estimate the entire probability density function in some sense, and I have to come up with an update for x based on y. And then those are called non-parametric methods. In other words, we no longer will parameterize our problems as being, okay, something with an unknown parameter. We will try to estimate the functions like p of x and y on a point-by-point basis. Okay, these are really, really powerful techniques that are typically not taught at this level, but they turn out to be the most effective in a lot of instances because parametric measurements or parametric modeling turns out to have a lot of limits when you're dealing with situations where models just simply don't apply. Okay, or models become just too complicated. So we will cover those in the last, let's say, all of the stuff that I just summarized for you, we'll cover those in the last, let's say, 3 lectures of the class. And then at the very last lecture, I'll probably do a review like I did for the midterm. We'll go over a bunch of problems and answer questions and whatnot. Okay? All right. So we'll stop here. Yeah, 5 minutes from now I'll be there, yeah.
I just want to follow responsibility.